Our next speaker, chemical researcher turned tech transfer professional with the talk that I'm personally excited about, university tech transfer and the problem with 5 to 10 years. Please welcome to the stage, James Leeland.
All right. Thank you for letting me talk here. So my name's James and I work in university tech transfer. So this is the part of the university that facilitates trying to get the research out of the lab and out into the world in the form of commercialization. What I'm going to do to talk to you today is talk about this problem with this 5 to 10 years. Quite often you'll see things, all different areas of science, you'll see it in the newspapers where they just go, oh, here's a thing, and in 5 to 10 years you'll be able to buy it, you'll be able to use it. So there's loads of examples here that I found: crop waste into petroleum products, renewable energy breakthroughs, treatment for obesity, absolutely loads of ones on cancer. One of my favourite ones I found, getting a dinosaur as a pet. 5 to 10 years, which leads on to an important question which is not asked to adults near enough. What is your favourite dinosaur? Ankylosaurus, and I will fight you on it. But anyway, what I did, I went with my colleagues that I work with and I gave them 30 seconds to come up with every reason why some of the projects fail. This is what they came up with. I'm not going to go through all of them, but two of my favourites: the lab burned down and the academic went to jail. But I'm going to concentrate on 4 of them here, and I'm going to go through these right now. First one, which is a big one: funding and the valley of death. So what you'll see in this very French-looking graph here is here on the bottom line, from the left-hand side, as you look at it, is the initial idea and the discovery. Going through the development, scale up, down to the commercial product where it's actually being made and it's out there in the world. What you find is here on the left-hand side with the university this is the initial research. This is where it's first done. And then at the right-hand side, it's the industry part where they fund it. They want to make the profit. They want to sell it. They want to make money. So starting on the left-hand side here with the university funds, as soon as they start to get away from the initial research, the funding bodies go, hang on a minute, this isn't fundamental research anymore. This is commercial. We're not going to fund this. This isn't what we should be using taxpayers' money for. But at that moment, it's really high risk to invest in it because they've made it maybe in a lab, in a round bottom flask, in a Petri dish, whatever. So industry looks at it and goes, I'm not going to touch that. That's way too risky. So the industry will only fund it once it's got through the other steps. So what you end up with is this lack of funding, this valley of death in the middle where it's too risky for industry to fund it because they want to be able to make their money, but also research councils might not fund it. Next one going into is a bit boring, but intellectual property. Now, there's lots of different forms of intellectual property protection. The one I'm going to talk about here is patents. Patents are a monopoly right to do something. It means you can stop someone else from doing what you have patented. One of the problems is no commercial investor is going to invest in something if you haven't got some form of IP protection, because otherwise what will happen is the industry will plough millions of pounds into trying to develop something, and as soon as they've solved all of the problems and get it out there in the world, someone will just come in, copy it. Nothing to stop them from doing it unless you have some sort of protection. Patents are expensive. They're cheap at the beginning, but it'll be 50 to 100k per patent within a few years, and it means that you've got to be careful what you patent. As a university with taxpayers' money, we can't patent everything. It'll cost too much. Final bit on the other side, just in case anyone wants to get a patent. To get a patent, at least in the UK or the EU, you have to have never spoken about it before in public at all, which means from an academic perspective, if you publish in a journal and then try and patent it, you can't. You've already let it out in public. Next one is progress and scale up. So imagine a graph. I've put catalyst efficiency on the y-axis, but it can be whatever you want. The main thing is you want to try and get to this target up here. If you hit that, that's where you make money. Time along the bottom, at the beginning, 5 to 10 years. People like to think this happens. It tends not to go this way. It might look like this. It's bumpy. You'll go a certain number of months, maybe even years, where you don't really make any progress, and then suddenly you'll go up, or maybe it'll look like this. This is something that's even more common. You go great guns in the first few years, but sometimes the last 5 to 10% of the problem is the most difficult, and sometimes you just can't get there. And then if you don't get across that line, well, you never see it. So it looks good, looks great initially, never quite reach it. Sometimes it can look like this. You can get there in the end, but instead of taking 10 years, maybe it takes 20. now this comes into the problem with venture capitalist funding, is they're not going to wait 20 years for a return on their investment. They're going to bin the project way earlier than that. So sometimes you can get there in the end, but it'll take a lot of funding to get there. So essentially what happens with this is a general problem with, in the lab on, say, a milligram or gram scale does not mean you can make it on a ton or megaton scale commercially. So at least not in a cost-effective way. And I'm wary of the location where I'm saying this, but look at graphene. Graphene is a wonderful material. It does amazing things, but no one can make it in huge scales cheaply to get it out there all over the place. What you find with graphene is that it is used out there. There are things there, but it tends to be used in more high-value niche-type applications. And there's hundreds, if not thousands, of reasons why things go wrong on scale-up. And essentially, it all boils down to there's always unknown unknowns, and something quite often goes wrong. Final part here, where I'm going to throw absolutely everybody under the bus, is the media. There is a bit of a lack of scientific literacy in journalism. I don't really blame them. They're under pressure. They've got to get it out. They've got to get the clicks. And sometimes they either don't care or, they just want to get it out there. And they often bury or ignore the details. So particularly with things like cancer or medical things, you'll see this wonderful new technique of doing it, but it's in mice or it's in a petri dish or something like that. They either bury it or just ignore it completely. The press offices, sometimes the press office of the university does do a really good job, but every now and again they can accidentally, or maybe on purpose, they overhype something. Again, they've got their own job to do. They've got to get the university's names out there. You can't blame them. Sometimes the communication's poor. If they give a list of 10 things, all of which are really valid, but the 10th one is, oh, but we haven't ruled out aliens, then the headline is, oh, could be aliens, and it misses all the rest of it. And then finally, everybody else, the public, everybody else. There is a bit of a lack of critical thinking sometimes in the readers, but also the problems with social media news, as it were. Sometimes, I'm sure not in this room, of course, but sometimes people see things as read. They'll read the title and they think, great, where is it? Where is this treatment that was supposed to be 5 to 10 years away that's now 20 years down the line? But all is not lost. Lab research does become a reality. There are lots of examples of things where things go from the lab all the way through the university, out into the world, and it is there. So often it does take more money than they think it is. It also takes more time than they think it does. It's also often the combination of lots of small, little incremental advances rather than just one giant leap where suddenly everything happens. It is also worth noting you do need a very good slice of luck. Sometimes you need to be in the right place at the right time, in the right field. And sometimes you've got to bear in mind, things can happen with a different application. You can start off thinking, right, I've got this thing, I'm going to commercialize this product into, into making a type of drug addressing one thing. And halfway down the line, you realize, actually, you should do something else. So it does get out that way as well. But if you do think about the advances that have been made in things like, cancer research, battery technology, solar and wind, things like that. These things are getting out there, so it's not all bad news. All right, and I'll come really quickly for me, so questions, nowhere near the horn.
Thank you, and we start with the question from James. Can't you already buy a dinosaur as a pet, or have the government got confused and outlawed Excel budget by mistake?
I suppose if you say like a crocodile or something like that, maybe you could get away with that, but I don't think you can get a dinosaur. Not at least not a fluffy kind, anyway.
So regular bird then.
Yeah.
The next question is from Anonymous. Nuclear fusion is normally 30 years away, not 5 to 10. Does it have the same set of issues, or is it a different one?
So when it comes to commercialization, you've got two different areas that sort of combine. One is risk, and the other is the potential market, the dangled carrot at the other end. With something like nuclear fusion, the dangled carrot is very big. It's unlimited, free, clean energy. Therefore, it might be worth putting in a bit extra money and accepting a longer time period. But at the moment, it's not really commercial. It is very much research based. I know that there are places, there are startups that are in the nuclear fission area, but they're generally running on grants. They're not making their own money at the moment. Sorry, there's someone who's disagreeing with me there. Do you want to say?
I do have a little bit of involvement in that there is a lot of private money gone into fusion in the last couple of years, and it is now back to 5 to 10 years.
Okay, I'll believe it when I see it. Sorry, that was that there is private money going into nuclear fusion, and now they're saying 5 to 10 years. So I will refer you back to previous graphs. But I will also caveat that by saying sometimes it really is 5 to 10 years, and it really does get through. And especially for things like nuclear fusion, I would love it to happen. Absolutely love it to happen. Will it be more likely to take 20 years? Maybe. I'm not a nuclear expert at all.
See you up here for the next talk in 10 years. I think we have time for the next question. From Anonymous again. If something that's been discussed publicly can't be patented, does it apply to anything that's been peer-reviewed?
If it is in a preprint journal or something like that, then essentially the question is, can a member of the public have seen it? So if the application process is first you send it to a journal, then it's peer reviewed, and then it's published, then you're fine at the peer review stage. If at any stage a member of the public can see it or read it, that's a public disclosure. You can't patent it anymore. So if it goes to a preprint server where it's before it's been peer reviewed, you've screwed it.
The next question is from Nick G. What is one study or product that you have been seen fall down the tech transfer that you think would be the game changer?
I wouldn't say, I'd say game changing is, sometimes you don't really know it. I mean, obvious things that have come out recently, things like CRISPR and things like that. If you talk about actual companies, I mean, there's loads of ones out there. So, I mean, there's a really big one might be like Oxford Nanopore is something that came out of Oxford University that do materials and also do. There's lots of businesses that do a lot of the genetic-based drug research, things like that. So, I mean, game changer, it could be nuclear fusion, it could be applications of CRISPR. I mean, AI is the big buzzword at the moment, to the point where I'm a little bit sceptical now. It's like there's some things that are amazing, but sometimes people are just throwing it out there. So, I mean, a bit of a waffly answer, but there's lots.
Okay. The question from Hieronymus Bosch. Does the last 10% problem make this fundamentally difficult to solve, even if value funding was available?
Yeah, funding is not the only option. I mean, the problem is the unknown unknowns. That difficult 10% that you can't get over might not exist. You might be able to get over it. But, you know, funding is... We have a duty to spend that money in the wisest way that we can. And at some point, if a project hasn't got that far, you've got to pull it. And if we don't pull it, more likely the venture capitalists that have funded it will pull it. The other thing to say is it's more about education. It's, you know, university academics don't go into university to try and commercialise a product. They go in there because they want to investigate, they want to understand, they want to learn. So trying to get that transition from an academic through to some sort of commercial product can be quite difficult.
One more question from some random guy, I don't know who. Is it the broad problem with modern scientific research, like publication bias and stuff, or is it something intersectional?
So what do you mean by intersectional there?
The intersection between science and industry, for example.
Oh, yeah, closer working between academia and industry would always be welcome. You know, I do think there is a role for the university in fundamental research. You never know what's going to come out of some of this stuff, so there is a role for it there. But as I said, yeah, funding will always help. Having closer links will always help. But you just never quite know what you're going to get.
The next question is from Anonymous. Do you have a personal favorite project that you wish could be brought to completion?
I do, but I'm not quite sure what I'm allowed to say.
Only legal things.
Well, yeah. There are projects that are in the team that I have that work on new ways of curing cancer. There are new ways of making particle accelerators to be able to make sort of proton beams to cure cancers. There are materials out there that do wonderful, amazing things. And that's as vague as I'm going to get.
Time for the last question, I think. From James. Can this sometimes be more conspiratorial, holding things like carbon capture as a solution that will allow us to keep fossil fuels?
Sometimes you do see it when you do the press release and you say, oh yeah, we've got this technology that could, for example, capture carbon. You do get people coming out going, oh, it's all fake. But I mean, you just ignore it. If you try and interact with it, you're onto a loser right there. You can just stick to the science, stick to the results, and go with that.
Thank you very much.